Here I describe for the basic theorems and approximations of LDA. Theorems and approximations. Approximations of LDA, DFT. And density function theory is a general term for calculating the band structure, and there's so many methods to calculate the band structure. And one example of the calculation of the band structure is LDA, local density approximation, and it is widely it is a general and widely used in the theoretical band structure calculation. And this density functional theory developed by the Hohenberg and Kohn and Sham, and three prominent scholars developed the density functional theory. The basic idea of the density functional theory is that effective potential is determined by the local density of electron, and therefore by assume that the local density determines the effective potential, and the effective potential is close to the atomic potential, then we can solve the Schrödinger equation. And how to solve the Schrödinger equation? And they developed a method to get the effective potential from the functional of electron density. And the only parameter of the calculation is the local electron density, because local electron density determines the effective potential. In Schrödinger equation, and potential is very important, and we do not know it depends on the potential, but potential can determine by the local density. Therefore, the only parameter of calculation is local density NR. And we know the Hamiltonian. Hamiltonian is composed by the kinetic energy plus and the Coulomb potential U and the extra potential V. In here we separate the potential as a simple Coulomb interaction, electronic Coulomb interaction. And secondly, it is the extra potential. And here we will deal with the basic idea, and basic principle for the Hamiltonian principle is that eigenvalue problem H psi and as a function of V is that EV and psi V, because the kinetic energy plus Coulomb interaction problem is widely known, and we do not know the extra potential, and the extra potential is very exceptional, and the Coulomb interaction is widely studied, and also we already know in the quantum mechanics, and also therefore this eigenvalue problem for the extra potential is critical. In this case, the electron density can be represented by the expectation value for the total wave function, and here psi r and psi r. Here psi is not it is a field operator, and here this psi is a field operator. Then here I will introduce very important and fundamental theorems without proof. And the first theorem of this, the first theorem is that external potential and the ground state are determined by local density. And the first theorem is that external potential VR and ground state psi V are determined by local electron density, and it means that in the VR and psi, here psi is a function of V, functional of NR. And here, and this energy state is also the function of local density, and also it can be calculated by the integral dr VR NR and plus extra functional form of the NR. And this here, the first one is that the expectation value of VR. It is the expectation value of VR, and this extra the extra term is the expectation value of T plus U. And here we then the T plus U is calculated from the quantum mechanics, and also this expectation of VR is very exceptional, and therefore this integration of V and R is very important. And anyway, this gives rise to the energy eigenstate. And the second theorem is that the total energy can be minimum when electron density becomes minimized and the correct ground state. And the second theorem is that the total energy is minimum when electron density becomes the ground state. Electron density becomes correct ground state, that the total number of electron is that volume integration of NR, volume integration of the local electron density. It is very natural, and also it can be generally accepted. And therefore here, because this functional f can be written like this, and it is a basic two theorems in the local density functional theory. And here the function of NR is the expectation of the T plus U, and also it can be write down as that kinetic energy. It is kinetic energy of free electron, and also here we should include the exchange energy. The exchange energy and also Coulomb interaction, and the Coulomb interaction can be write down as 1/2 integral dr prime, and also r minus r prime, and also nr and nr prime. And here, the first term is the kinetic energy of free electron, and the second term is the exchange correlation energy. And the third term is the Coulomb interaction. Because in the volume integration nr, and it gives rise to the total charge. And also here 1/2 is coming from the double counting, to exclude the double counting, because 1 and 2 and 2 and 1 interaction is identical with each other. Therefore, then it is the only thing that we include the exchange energy. And here before that, the Thomas-Fermi model do not take into account the exchange energy, but in here we include the exchange energy. Then the total energy, here the total energy EV is the total energy for it is also is a function of local density, and it is that Fs plus VR here is integral dr, and the VR and R, we know that it is that, and also plus here F and R is when you write down an R, and plus exchange energy, and let's write down is 1/2 before dr prime and r minus r prime and nr and nr prime, and also plus exchange energy. Then here from this term until this term, we call it is a Hartree energy. And here Hartree energy plus exchange energy is the energy eigenstate. Here this energy should be minimized with respect to the local electron density. Therefore, and here we should calculate that partial EV, it is NR function, and the partial NR. Then it is that this term should be calculated, and also here delta TS NR over delta NR, and also this term becomes that potential VR, and the derivative with n on this term, this third term, is the plus integral dr cancel, and because nr is can be omitted, can be cancelled by the derivative, and also here nr prime and r minus r prime and dr prime. Here 1/2, we do not have the 1/2 in the prefactor, and the absence of 1/2 means that there is no double counting, because only NR, not NR and NR prime, and therefore in the exchange energy term plus delta energy exchange NR over delta NR, And here, let this one has the potential phi r. It is potential energy, and it is exchange potential energy. And here, let's denote that the phi r is that VR plus Coulomb interaction, R minus R prime and R prime, the R prime, and also exchange potential can be write down delta EX NR over delta NR. Here is the potential energy, and it is exchange potential energy. Then from this one, and also we can think that the number derivative of energy, it is from the definition, it is a chemical potential. It is a chemical potential mu. Therefore, then we already describe only this, and this the first term is that delta Ts NR over delta NR plus, and the phi we denote it as a phi r, and plus exchange potential R, and also here that this potential comes to this term, therefore minus chemical potential equal to 0. Therefore here it is potential and it is exchange potential, and the potential plus exchange potential is the effective potential. It is effective potential. And therefore by using this, the Cornish self-consistent single particle equation, and it is that we can know that by using this equation, and we can get this Schrödinger equation. And here Cornish makes the self-consistent single particle equation, is that minus h bar square over 2m del square plus effective potential psi IR equal to epsilon I psi R. And also this effective potential also is a function of local density. It is NR functional. Here, and how to solve this problem, then here we the basic idea on this density functional theory is that all terms is determined from the local density. Therefore local density is very important, and the local density is write down from I to 1 to n, and psi I R square. It is here I is the energy eigenstate, and also it is a definition of the local carrier density. And also this energy, all the energy term can be write down for the expectation value phi I, and also here the kinetic energy term from this Schrödinger equation, and it is h bar square over 2m del square plus effective potential, and psi I, it is the expectation value, can be write down the total energy. Then it is total energy is that the kinetic energy as a function of local density plus effective potential and the dr for effective potential. And from the definition, this is a kinetic energy, and the second term is that this because the definition, and it is nr. And therefore, then this kinetic energy is that summation for epsilon I minus integral dr, and also the effective potential. What is the effective potential? And the effective potential is the phi plus v exchange energy. Then phi can be write down this. Phi can be write down this, and also is exchange energy. And therefore, I will write down in explicit form. And the first term Vr plus integral dr prime and the Coulomb potential nr prime, and also r minus r prime, and also V effective potential and r. The first term is phi. The first and second term is phi, and the third term is effective potential, and it's nr. Then we can say we should solve the total energy. Where is total energy? The total energy comes from this one. And here it is a calculation of total energy, and we here from this one, and from this one, the total energy as a function of nr is that ts can be here summation for epsilon I minus integral dr, and also vr nr, and this one coming from this, and here, and then like this, and minus integral dr prime nr and nr prime, and also r minus r prime, and minus the third term is dr n nr v effective r. It is a ts term, and also it is only ts, and we should include this one exchange in this, and plus 1/2 integral dr prime nr prime over r minus r prime, and also plus exchange energy nr, and also finally this term plus integral dr vr nr. And from this, and these cancel with each other. Therefore, let's summarize. It is summation I here, and it is minus 1, and it is 1/2. Therefore, it is minus 1/2 integral nr prime and r minus r prime dr prime, and plus exchange energy nr minus integral dr nr v exchange r. And here this total energy also can be obtained when you get the local electron density here, because And when you see this, and this exchange potential and exchange energy and the Coulomb potential and the summation, the total energy, also all this term coming from the local density, and therefore we call it is a local density is very important. Then the local density approximation. Local density approximation, we call it is LDA method, and there is some assumptions. And the assumption is that electronic density, the electronic density slowly varies in space. And here exchange energy and is coming from the for integral over space, and exchange energy and NR. And here this we know that let's assume that this exchange energy is known from a given NR, and it is assumption. Then here when it is a local density approximation is that electron density slowly varies in space. Then the total energy can be written down from the above, summation epsilon I minus 1/2 integral dr prime nr prime and r minus r prime, and plus here it is this term is that the exchange potential, and it is exchange energy, and therefore, and here integral dr nr, then exchange energy minus exchange potential. And anyway, and the exchange energy and exchange potential is different, because potential is potential, but the energy contains from the potential and kinetic energy, and therefore the energy and potential is different. And also then here when you think that this exchange potential, and here exchange potential is that number derivative of the exchange potential in NR and it is exchange correlation potential. We define that it is a mu EX. It is also kind of in mathematical formula says that physical interpretation, it is energy, and it is energy, and the number derivative, it is chemical potential. And anyway, chemical potential is also energy, and it is exchange correlation potential. And therefore, and here the here the exchange correlation potential, then anyway we do not know exactly, and also but in some cases we should have we should make assume that the exchange energy and exchange potential We don't know exactly. And also, therefore, there are several methods to solve these equations. And also, this LDA is good for the electronic system with homogeneous charge distribution because it assumes that electron density slowly varies in space. And also, exchange energy, even though it considers for the exchange energy, and the exchange interaction is should be very small. But there are many. Therefore, then we should adopt for different assumptions. And also here, and I will say that the LDA is good for the first one is the homogeneous charge distribution. For the cases that homogeneous charge distribution, and also second, small exchange interaction. And also, therefore, then it is good for the ground states of s and p orbitals. And also, then in magnetic elements, iron, cobalt, nickel, and metallic ground state. Yeah, also then the excited state, and the excited state can be calculated by the Dyson equation. And the excited state can be calculated by Dyson equation. Dyson equation is the modified theory from the Schrödinger equation, and the Dyson equation say that minus h bar square of 2m Laplacian plus VR plus integral dr prime nr over nr prime over r minus r prime psi I r, then plus integral dr prime, and here this sigma is not the sum but it is a self energy, and r prime, and also with epsilon I and psi I r prime, then it is that epsilon I psi I r, then we call it is a Dyson equation. And also here we do not know in detail, but anyway, this we call it is a self energy of quasi-particle. Self energy of quasi-particle. And here this self energy is kind of exchange interaction potential. Here, the self energy is a function of r and r prime and epsilon I, and is kind of exchange interaction potential of an electron from the other electrons. And also this function this function makes that it is a non-local correlation. And also this self-energy is related to the exchange potential, and also it is modified Schrödinger equation, and also therefore this at finite temperature the thermal excitation or the thermal excitation and also different chemical potential can make a different exchange energy, and it is excited state of Dyson equation. And basically this Dyson equation and also the solving this Dyson equation is that we call it as a GW we should use that GW approximation, and the GW approximation will be introduced later. And here we use the green function. We use the green function to calculate more exactly. And also energy band gap obtained by the LDA calculation, it underestimate the real band gap, and it means that the band gap calculation are small comparing to the real energy band gap. And it is a widely known problem, and that's why the electron excitational band gap case is that one electron in a balanced band moves to the conduction band, and also this in real cases, and LDA just assumes that the number of electrons is fixed, but in fact, and the number of the charge excitation can make extra exchange coupling, and that's why in excited state the energy band gap underestimation is coming from the exchange energy difference in the excited state. And here, then we do not know that the problem is that we do not know this exchange interaction term, self-energy term, and this self-energy term can be obtained from the GW approximation. Here, GW approximation, and here we do not know to obtain this self-energy, and we use the GW approximation. And here G means that the green function, and the W means that the effective potential, and therefore and the GW approximation can make this kind of self-energy term, and this self-energy term and the Coulomb potential and the exchange potential, and we can calculate this Dyson equation. Anyway, then this local density approximation and the density functional theory should be calculated by the numerical calculation, and not mathematical calculation. Therefore, we should use the computer program.